Hello.
Hello.
How are you?
I'm bad.
Hello, Sarrah. So welcome. So let's start with, we had a meeting this week, DevoWorm, and we didn't have any other meetings. Let me go over the DevoWorm YouTube channel. That's where all our meetings are posted. So we've been going, we'll be on our 8th meeting on Monday this year. So we've been covering a number of topics from early January. We're talking about epithelial tensegrity. We talked about a paper called the BAAI worm approach, which is the brain-body environment, a model of C. elegans that takes all of that into account. We've had a couple discussions on developmental hypergraphs. This is something that Mehul Arora worked on last year, and he's wanting to develop it further this year. We've been talking about connectomics and computational methods for connectomics and C. elegans. Different types of patterning codes in the lineage tree, different topics in evolution and in bioelectricity. And, so we've covered a number of topics in our weekly meetings, and those are on Mondays, and then they're posted to YouTube. Then I did a lecture, I think it was this week, where, I've been working on these slides for a while, and I just finally decided to do the lecture I record the lecture. And so this is called Interactive Morphogenesis, Source and Dynamics of Moir Pattern Formation. So this is something that involves using Moir interference patterns and other types of layered morphogenesis, and to demonstrate pattern formation, to describe pattern formation, and showing examples from nature where that happens. So that's on our DevoWorm YouTube channel. Check that out. The first thing is this. I've had this collection of things for a while, and I wanted to clarify this concept as we talk about large language models, but also as we talk about bio-inspired models and think about what they call shot learning in deep learning, but in other types of learning models. So this is the definition from Wikipedia for zero-shot learning. So zero-shot learning is a problem set up in deep learning where at test time a learner observes samples from classes which were not observed during training. It needs to predict the class that they belong to. So this is where you either have some sort of generalization or you have unsupervised learning where you have not seen this, or the model has not seen this before, and you have to correctly classify. So the learner observes samples from classes which were not observed during training and needs to predict the class that they belong to. The name is a play on words based on an earlier concept of one-shot learning, which we'll talk about in a minute, in which classification can be learned from only one or a few examples. So zero-shot methods generally work by associating observed and non-observed classes through some form of auxiliary information, which encodes observable distinguishing properties of objects. For example, given a set of images of animals to be classified, along with auxiliary textual descriptions of what animals look like, an artificial intelligence model, which has been trained to recognize horses, but has never been given a zebra, can still recognize a zebra when it also knows that zebras look like striped horses. So this both sounds like you can do some sort of transfer learning, or generalization, but also can get you into trouble if you think that something looks like something and it doesn't. So if you have, you might fall prey to false positives, but as a shortcut to learning, it's fairly effective. So this is a problem that we have, it's an outstanding problem in computer vision, natural language processing, and machine perception. So I don't mean to do an exhaustive review of it here, but I wanted to talk about this, and so we can talk about it, get it clear in our minds what this is. The first paper on zero-shot learning and natural language processing appeared in 2008 at the AAAI, but the name given to the learning paradigm there was dataless classification. The first paper on zero-shot learning and computer vision appeared at the same conference under the name Zero Data Learning. The term zero-shot learning itself first appeared in the literature in a 2009 paper from Palatucci, Hinton, Pomerleau, and Mitchell at NIPS 09, which is now NeurIPS. This terminology was repeated later in another computer vision paper, and the term zero-shot learning caught on as a takeoff on one-shot learning that was introduced in computer vision years earlier. So in computer vision, zero-shot learning models learn parameters from seeing classes or observed classes, along with their class representations, and rely on representational similarity among class labels so that during inference, instances can be classified into new classes. So you're observing a subset of things, you're exposed to a wider set of things, and the model has to generalize, say, from horses to horses with stripes, which are now zebras. So you can have this new category and give it a new label. In natural language processing, the key technical direction developed builds on the ability to understand the labels. That is, represent the labels in the same semantic space as that of the documents to be classified. So these labels are in the semantic space and they're connected to one another. This supports the classification of a single example without observing any annotated data. The purest form is zero-shot learning. So this is where we don't have any labels at all. So that's the purest form of zero-shot learning. The original paper made use of the explicit semantic analysis representation, but later papers made use of other representations, including dense representations. This approach was also extended to multilingual domains, fine entity typing, and other problems. Moreover, beyond relying solely on representations, the computational approach has been extended to depend on transfer from other tasks, such as textual entailment and question answering. Okay, so yes, then the original paper also points out that beyond the ability to classify a single example, when a collection of examples is given with the assumption that they come from the same distribution, it is possible to bootstrap the performance in a semi-supervised manner, or what they call transductive learning. So this is where we have these three components. We have the visual or the image properties, the features, the feature space. Then we have our labels, which is embedded in a semantic space. And then we have this distribution, which is the distribution of these examples and their likelihood or their probability. So this is kind of an interesting way to think about this. This is where it comes from. So that's zero-shot learning. Now we talk about one-shot learning. So this is one-shot learning. And again, this is an object categorization problem. And so whereas most machine learning-based object categorization algorithms require training on hundreds or thousands of examples, and so again, with zero-shot learning, one-shot learning is sort of a shortcut to learning. And again, it could result in a lot of false positives, but it can also help you in cases where you need to pick up, you need to figure out what something is. One-shot learning aims to classify objects from one or only a few examples. So this is where you're not doing unsupervised learning. You're not doing raw generalization where you're just trying to, find a new thing from no examples. You actually have one or maybe a few examples. You have a very sparse set of data to learn from, and then you have to learn correctly. And that's up to the model. That's up to the model's capabilities. The term few-shot learning is also used for these problems, especially when more than one example is needed. So The ability to learn object categories from a few examples at a rapid pace has been demonstrated in humans. And so this is something that we see in development. A child learns almost all of the 10 to 30,000 object categories in the world by age 6. So in development, you acquire the semantic space and you acquire these labels for things. And as we talked about this in the data sets that exist for children or that were acquired from children, where you have these natural scenes, and then you also usually have some semantic component or some complement of linguistic data that are attached to that. So we have labels as well as images and features. This is due not only to the human mind's computational power, but also to its ability to synthesize and learn new object categories from existing information about different previously learned categories. Given two examples from two object categories. One, an unknown object composed of familiar shapes. The second, an unknown amorphous shape. It is much easier for humans to recognize the former than the latter. So it's easier for us, I guess at least in development, to recognize an unknown object composed of familiar shapes. And of course, we know this from cognitive science, where you give people these different geometric primitives and they can identify them and put them together and give it a name. And then the second is an unknown amorphous shape. So if it doesn't contain these geometric primitives, they don't, people can't necessarily get a fix on what it is or what it might be. And so again, you have this potential for false positives, but it's also something that, you could fit into these broader categories, into these broader schema that we have. So it is much easier for humans to recognize the former than the latter, suggesting that humans make use of previously learned categories when learning new ones. So this is about category learning, where you have objects, they have familiar attributes. Those features then can generalize in terms of like knowing what features are combined in what way, and then expanding that semantic space or that category space to new things. So, the categories are necessarily linked. So you're using previously learned categories to form new categories, and they're linked in that way. The key motivation for solving one-shot learning is that systems like humans can use knowledge about object categories to classify new objects. So they're, making this analogy from human development, from human learning. And so, as with most classification schemes, one-shot learning involves three main challenges. So the first is representation. How should objects and categories be described? Then there's learning. How should such descriptions be created? And then there's recognition. How can a known object be filtered from enveloping clutter, irrespective of occlusion, viewpoint, and lighting? So recognition is isolating the feature. Learning is sort of the sort of schema for creating new descriptions, and then representation is how do you merge that feature space and the category space. One-shot learning differs from single object recognition and standard category recognition algorithms in its emphasis on knowledge transfer, or transfer of learning, which makes use of previously learned categories. All right, so again, there are different things like thinking about the model parameters. We want to reuse model parameters. There's a similarity between old and new categories. Categories are first learned on numerous training examples. Then new categories are learned using transformations of model parameters. Those initial categories, we're selecting relevant parameters for a classifier. Then there's feature sharing, which allows us to share parts or features of objects across categories. And the concept of mutual information is important because those features those features are going to have some mutual information. That mutual information is going to make that linkage between the old and the new category. So if you have, like, for example, these geometric primitives and they exist in this new category, then that classification will be based on sort of the shared geometric primitives. So a dog category, for example, may be learned in one shot from previous knowledge of horse and cow categories, because dog objects may contain similar distinguishing patches or these geometric primitives. So you wouldn't classify a dog in the context of like a marine invertebrate. You'd classify a dog in the context of a quadrupedal animal, a horse or a cow. And so we have this, there are different ways you can do this sort of transfer, but it's the way it's usually done in models, in machine models. Then there's contextual information, and this appeals to global knowledge of the scene in which the object appears. Such global information can be used as frequency distributions in a conditional random field framework to recognize objects. Alternatively, context can consider camera height and scene geometry. Algorithms of this type have two advantages. First, they learn object categories that are relatively dissimilar. Second, they perform well in ad hoc situations where an image has not been hand-cropped or aligned. So this has a lot to do with Bayesian theory, and again, we have this probabilistic or likelihood model. So Bayesian one-shot learning algorithms represent the foreground and background of images as parameterized by a mixture of constellation models. During the learning phase, the parameters of these models are learned using a conjugate density parameter posterior and variational Bayesian expectation maximization, or VBEM. In this stage, the previously learned object categories inform the choice of model parameters by a transfer by contextual information. For object recognition on new images, the posterior obtained during the learning phase is used in a Bayesian decision framework to estimate the ratio of object given test or train. So with the likelihood of an object given test or training to the ratio of that to the likelihood of background clutter given test or train. So basically you're testing the background versus the object, or the signal versus the noise given your training data set and your testing data set. P is the probability of the outcome. Okay, so this is basically more about the Bayesian framework, and I'll skip that. Now I'll go to these last two things that I wanted to talk about. This is a medium post on few-shot learning. And so we have zero-shot learning, which is learning from sort of de novo. We're learning from other categories completely. We're not observing anything. We have one-shot learning, or maybe a few-shot learning, where we kind of pick up from maybe a few examples, a very sparse set of examples. And then we have n-shot learning, which is where you have to add in examples and you keep adding in variation in the observations of a thing. So if we want to classify a specific breed of dog, we need to have quite a few more examples than just of a dog. And so this is where we have this distinction between sort of this unsupervised learning, this sparse supervised learning, and then supervised learning where we have a rich set of examples. And the idea is that the model sensitivity to that is what people are always trying to optimize on. So in the field, people are always advertising zero-shot learning, or one-shot learning is really the standard. But it's interesting to think about some of these examples, with biologically inspired models where you have, maybe the case where it's better to have n-shot learning than to have zero-shot learning. And so, just something to think about. In any case, this article on Medium, this is few-shot learning, this is WMSI, and this is an article on few-shot learning. Specifically, few-shot learning stands out as a revolutionary progression in the field of machine learning, allowing models to undergo training using a minimal number of labeled examples. In contrast to traditional supervised learning, which relies heavily on abundantly labeled data, few-shot learning addresses this challenge by furnishing models with only a small set of labeled examples per class. This strategy involves utilizing a support set for training episodes, enabling models to excel in tasks where data availability is restricted, particularly in domains like clinical natural language processing, or NLP, clinical NLP. This exploration delves into the transformative potential of few-shot learning in the context of NLP. The article covers various aspects, including an overview of few-shot learning, the mechanisms behind few-shot learning, and few-shot learning specifically relevant to NLP. In NLP, we use few-shot learning or zero-shot learning, and there's a comparison there. Then there's narrow AI, defining general AI, which of course we talked about general AI last week, and sort of how that can be distinguished from narrow AI, especially as a goal of research. Then insights into data labeling and an exploration of data labeling tools. Let's talk about the examples of few-shot learning in NLP. So these are meta-learning approaches, and the first example are what they call Siamese networks. So Koch et al. 2015 introduced Siamese networks to determine the likelihood of two data examples belonging to the same class. These networks use identical multi-layered neural networks to process examples, creating embeddings. The distance between these embeddings is computed and fed into a comparison network for classification. So in training, pairs of examples are randomly chosen from a broader set of training classes, encouraging generalized learning. In testing, entirely different classes are used, aligning closely with the spirit of N-way K-shot tasks. So this is where you have multiple ways that you can view the thing, and then you have different shots of tasks. So there are different ways you can sample the data as well as being exposed to the data. Applied applications applied in NLP tests such as question answering and text classification, focusing on semantic similarity or dissimilarity between text inputs. The next example is prototypical networks. So Snell, 2017, introduced prototypical networks, addressing data imbalances by creating class prototypes through embedding averaging. Classification is based on the similarity between prototypes and a query embedding calculated as negative multiple of Euclidean distance. So the application of this is used to address data imbalances and applied to name entity recognition tasks in a variation proposed by Bin et al. Then we have matching networks. So Vanyos et al. 2016 proposed matching networks, predicting one hot encoded labels for our query set through a weighted sum of support set labels. Weights are determined by similarity computed through cosine similarity between embeddings generated from separate networks for support and query examples. This is employed for N-way K-shot learning tasks, predicting labels for the query set based on the support set. Then the challenge is that it's susceptible to data imbalance, where classes with more support examples may dominate. Then you have non-meta learning approaches such as transfer learning, prompting, and latent text embeddings, and that's all for that. So that's some examples of how this works. And then finally, I want to get to this paper here. This is few-shot learning. It's a survey of the field. So this is a comprehensive survey of few-shot learning, evolution, applications, challenges, and opportunities. This is Yixing Song, Ting Wang, Subroto Mondal, and Jyoti Sahu. So this is the abstract. Few-shot learning, or FSL, has emerged as an effective learning method and shows great potential. Despite the recent creative works in tackling FSL tasks, learning valid information rapidly from just a few or even zero examples still remains a serious challenge. In this context, we extensively investigated more than 200 latest papers on FSL published in the past 3 years, aiming to present a timely and comprehensive overview of the most recent advances in FSL, along with impartial comparisons of strengths and weaknesses of the existing works. For the sake of avoiding conceptual confusion, we first elaborate and compare a set of similar concepts, including few-shot learning, transfer learning, and meta-learning. So meta-learning and transfer learning are distinct from few-shot learning. Furthermore, we propose a novel taxonomy to classify the existing work according to the level of abstraction of knowledge in accordance with the challenges of FSL. To enrich this survey, in each subsection we provide an in-depth analysis and insightful discussion. Taking computer vision as an example, we highlight the important application of FSL, covering various research hotspots. Finally, we conclude the survey with unique insights into the evolution of these technologies and kind of hope that that gives us guidance for the future. So let me see if we have, okay, so this is kind of getting into the concepts, talking about FSL, which is few-shot learning. And so they say, what is few-shot learning? The concept of few-shot learning is inspired by the robust reasoning and analytical capabilities of humans, and it is widely found in edge computing scenarios. So few-shot learning is taken from humans, but I think we could say that you can also find examples in other animals and other learning organisms, and maybe that's something that is done better in other organisms, in other model organisms. Or we can take look at the variety of few-shot learning across organisms. That would be kind of an interesting topic to follow up on. In 2020, Wang et al., and that's reference 5 here, give a detailed definition of FSL through experience, task, and performance of machine learning, which is one of the most recognized definitions so far. So that definition is, a computer program is said to learn from experience E with respect to some classes of task T and performance measure P, if its performance can improve with E on T measured by P. So it's improved by experience on some task measured by the performance measure. Okay. It is worth mentioning here that E in FSL is very small, so experience is small, the task is variable, or maybe it's the same for your specific measure of it, but it would vary across tasks, and then your performance measure would vary across tasks as well. So your performance measure will vary by task, and if experience is variable, then it varies by that as well. In recent years, relevant neuroscientific evidence in citations 6 and 7 has shown that innate human capabilities are related to various memory systems, including parametric slow learning neocortical systems and non-parametric fast hippocampal learning systems. So they're talking about slow learning in neocortex and fast hippocampal learning, which correspond to FSL's database slow learning and feature-based fast learning. So this is where you have this database learning versus this feature-based learning in few-shot learning, and then that corresponds with different parts of, I guess, the human brain. To better understand FSL, it is necessary to introduce 2 concepts. So we already talked about N-way K-shot, which is a open type of problem, and then the other is cross-domain few-shot learning. So the N-way K-shot problem is often used to describe the specific problems encountered by few-shot learning. In this case, the support set represents the small data set used in the training phase, which generates reference information for the second phase of testing. The query set is the task on which the model actually needs to predict. Notice that the query set classes never appear in the support set. So classical N-way K-shot represents support set with N categories and K samples per category. So you have categories with samples in each category. Then the whole task, by way of that, has N times K samples, as thus N-way one-shot learning represents one-shot learning, and n-way zero-shot learning represents zero-shot learning. So you would have, in n-way one-shot learning, you would say have 10 categories, 1 sample per category, giving you 10 samples. And then n-way zero-shot learning would be 10 categories with 0 samples in each, giving you 10 samples of classes with nothing as a reference point, and you would have to generalize from that. The concept of cross-domain originates from transfer learning, which refers to the transfer of the knowledge from the source domain to the target domain. There usually exist domain gaps between these domains. Cross-domain few-shot learning integrates the features of cross-domain and few-shot learning. It is a challenging direction that has recently emerged. Okay. So this shows one of the knowledge graphs here for few-shot learning. One-shot learning and zero-shot learning are keywords to relate the main advances in research directions in the field of few-shot learning in the recent last 3 years. So this shows examples of these things in the literature. To be clear, this is one-shot learning, this is zero-shot learning, and this is a literature graph where we're looking at different topics related to these different types of learning. So, of course, you have machine learning, gesture recognition neural networks around one-shot learning. You have computer vision in there. You have zero-shot classification. You have Siamese networks, which you talked about. We have online learning. We have information literacy. We have supervised learning, image recognition. So this is just kind of a literature search. And then the number of FSL-related papers published in prestigious journals from 2010 to the first half of 2021. So this looks like it's becoming a hot topic with, I guess, probably hundreds of publications at this point. In 2011, there were less than 20. So it gives an idea of what people are thinking about in the field. So what is meta-learning and how is it different from few-shot learning? So meta-learning is a general learning paradigm that provides training on tasks and an episodic training mechanism. They talk about this in Figure 4. Meta-learning focuses on improving generalization for unseen tasks using prior knowledge. If prior knowledge is used to teach the model how to learn on specific tasks, meta-learning can be regarded as a variant of FSL. It is emphasized that meta-learning is not equivalent to FSL, but FSL should rather be seen as the ultimate goal. So you might use meta-learning to get to FSL, but it isn't equivalent to that. It aims to achieve robust generalizations without relying on a large scale of data sets. And by dual sampling of data and task space, meta-learning is enabled to construct a large number of auxiliary tasks related to the unseen task. So this is where you can improve the model's performance by using meta-learning. And it involves a number, so it involves 3 steps. Stage 1 is where you find the learning algorithm and see if it can produce a specific function. So you have these tasks and they should produce a function. And you can use this for, you can use learning rates, initial parameters, and network architectures to derive this function from the tasks. Stage 2 is where you define a loss function using the tasks. So you have task 1, you have the prediction, and you compute the difference. So you take performance versus a prediction, observed versus predicted, and you compute the difference there, and that's your loss function. And again, this involves network architectures, initial parameters, and learning rate. And then stage 3 is where you find the parameter that can minimize the loss function. So you use some classifier that can minimize the loss function. This involves gradient descent and reinforcement learning. So that's what meta-learning, or meta-learning is, and there are different variations on it, like meta-reinforcement learning, meta-video detection, and so on. So I think that's enough on that topic. I just wanted to go over that, and I wanted to think maybe more broadly about this now that we have some of the fundamentals down on that. So, for example, we're thinking about models. We're thinking about how they learn, but we're also thinking about how we have to train them to get them to learn. And so, we talked about developmental data. We've talked about we've talked previously about how development is different from, say, like adult learning. That, in adult learning, or at least in a model that we have that's analogous to adult learning, we would use a number of different, we would just present examples, say, of images. We might use an image database with labels or without labels, and we assume that the model can generalize. And then, of course, we've seen these developmental data sets where you have these labels, but you have to generate new labels. And we usually use this continuous scene data where, it's a very different form of exploration than in the adult analogous data sets. And then, of course, the whole question of how do we synthesize categories, and how do models and organisms, but also models, recognize things that can be categorized. And I mean, anything can be categorized, but it seems like there's this bias towards things with a clear structure, and perhaps a structure that's familiar to the model or the organism. So it's not that you have this amorphous thing that can be easily classified. And, that's just kind of a matter of decomposing the object into different smaller pieces that are similar to other things that have been learned. But also having this sort of semantic space and this feature space that are linked, and having that as a reference point. So, okay, so do we have any thoughts on that?
I mean, I certainly think, like language learning and kids is a good example. I think it might be a good example of that. There's actually several learning systems in a developing child.
Yeah.
And that they are sharing some larger context space. Because what we know is that they seem to be quite good at kind of one-shot learning, or as well as like super rapid learning. Yeah. That it reflects that, where it's supposed that there's some inductive bias that's it's probably biology, and then it becomes something else. It becomes something else that's used, or it's something that becomes more conceptual, or again, like you've got that mix of kind of cognitive researchers who aren't kind of worried about the neural representation. And so they're just dealing with the behavior. They're impressed by the young child's generalization and other kinds of behaviors when put in experimental scenarios, right? I mean, this is why cognitive development is so interesting, or should be of more interest to all these meta learning groups and it's like continual learning is something that seems to have become a field because neural networks didn't work. And cognitive development is certainly developmental psychology is more the field of like, here's a biological neural network that's doing it, is always on, is learning multiple tasks, and and relating them more and more, not even necessarily when they should be related, and again, it's always fascinating to, as Piaget did, right? It's always fascinating to listen to kids playing, and especially playing make believe.
Yeah.
Because it's it's fascinating window into how they connect things and how they think things work, and all sorts of insights into potentially how it's working behind the scenes. But of course, it just needs more. It's actually really difficult to bring out experimentally, right? But you can just tell that there's a lot more going on than on our than our very abstract maths.
Right. Also interested in kind of how this might be linked to a generalized mechanism of associative learning or Hebbian learning, and I don't know, to think about that a little bit as well. But yeah, there are a lot of connections here with different learning systems. So like, the assumption here was we're just talking about a single model. And, you might have multiple learning systems that are engaged simultaneously. So if you have like a semantic space, that's a language circuit or a language model. And then you have the visual examples or the computer vision examples, which is a learning or a visual module. And then there are other things as well, different other systems that are involved with that. Of course, there's memory, which is the hippocampal circuit. There's spatial cognition. There's movement. So, when we incorporate embodiment into things. So there are a lot of systems that are engaged simultaneously. But, we're just talking about a single model here. But, in an organism, you'd have multiple models simultaneously.
For sure.
Yeah. So Sarrah asked, based on the same concept, in-shot prompting and one-shot prompting are heavily used in prompt engineering for large language models as well. So yeah, that's a thing. I didn't talk about the prompting. There was a section, I think, in the review on prompting. So I'll post the link to the papers in the Slack and then put it in the description of the video as well. So you can read more on that. Okay, the next thing I wanted to talk about, a series of posts by Melanie Mitchell. And I believe this is on her Substack. And this is on large language models and world models. We talked about this, I think, last time. We've kind of been following up on this topic over a number of weeks. So we've been talking about large language models and reasoning. So this is on large language models and world models. This is part 1. I'll talk about part 2 next. How do large language models make sense of their quote-unquote worlds? So this is where you have a model, and then it's embedded in the world, and they have to make sense of the world through that, through some sort of world model. We talked about world models could be kind of going back to good old-fashioned AI or symbolic models, and so in that sense, it's not really anything new. On the other hand, you can also have world models that are, just kind of a list of things outside of the experience of that model. So if you think about generalization, we just talked about with zero shot or one shot or few shot learning, a world model can improve upon that performance on those kind of tasks because it gives you a framework for inferring things in semantic space. So this is kind of a reflection on some of these world models and how they might apply to large language models. So she talks about AI brittleness in the before times. So in the long ago times, before large-scale generative AI came onto the scene, machine learning systems had some problems. The first is often they didn't learn the general concepts we were trying to teach them, but rather solve problems using shortcuts or surface heuristics. So one example of this is where some researchers tried to train a deep neural network to classify skin lesions in photos. This is an example. And they tried to classify them into benign or malignant. Obviously, we want to know the difference. We use different features of the images to get an answer and then match it with the real world diagnosis. While this network performed well on these kinds of photos it was trained on, the researchers noticed a problem. So that problem was the algorithm appeared more likely to interpret images with rulers. So you see that there's an image here, and this is a clinical context where you put a ruler there to measure the size of they'll put that in the image so that the clinician can estimate the size of the lesion. And the rulers were in the images. They were more likely to interpret images with rulers as malignant. Why? In our data set, images with rulers are more likely to be malignant. Thus, the algorithm inadvertently learned the rule that rulers are malignant. So when you have a ruler here, and maybe they're putting the ruler there because they want to measure, because they notice that it's generally bigger than other lesions, and they want to measure it. And they put it in the image. So this is an artifact of the image acquisition. So you're acquiring clinical images. You have the ruler, which is irrelevant, not necessarily relevant to the diagnosis, although it does have some correspondence with the diagnosis. There is some correlation there, simply because of practice. It's classifying everything with a ruler as malignant. Now, of course, the problem there is that it's not always going to be malignant. So, again, we're getting these false positives where we shouldn't be because the model is taking some shortcut. And so that introduces a problem. And that is if you're acquiring data in the real world and you see something associated with something else, it's easy enough to say that, well, of course, that's a feature of a certain outcome, but it may not be that simple. So, basically the network learned a useful heuristic, but it wasn't that useful in the end. The network didn't understand what a lesion is, or what motivated the researchers to train it, or why rulers might be seen in particular images, or anything else about the world. So this is where we want to introduce this world model. Heuristic shortcuts are okay, but they also have to be weighed against realities of the world that that image is taken from. So such heuristic shortcuts weren't limited to visual data. In 2019, one group reported on using a neural language model to determine whether one sentence logically implied another. The model performed very well in a data set designed to test this general ability, but it turned out that the model's high performance relied on superficial syntactic properties, or this syntax space, on such as how the words in one sentence overlapped those in the second sentence. When the network was given sentences for which it could not take advantage of this heuristic, its performance decreased dramatically. So this is where it picked up on some feature of a sentence structure, and it used that to classify things. And of course, it doesn't generalize because that structural feature isn't available in a language. You could imagine training a model on like some structure of poems and then unleashing it on a corpus of text that doesn't involve poetry, but instead involves like nonfiction or even fiction literature. So it's just a different style of writing, and where it's trained in one case, it can't distinguish between different styles of writing, basically. Another group wrote about similar brittleness in a deep reinforcement learning system that had successfully learned to play the Atari video game Breakout. The system was trained by being given video frames from the game and then choosing actions, moving a paddle horizontally to bat a ball in order to hit exploding bricks. While a trained system seemed to be highly skilled at the version it's been trained on, the researchers showed that small changes in the game, such as moving the paddle's vertical position by a few pixels, caused the measure of performance to plummet. It seems like the original system had learned the abstract notions.
Sorry, Bradley. There's something including the text on the
I know
on the right.
It's the way I captured it. Yeah.
Oh, okay. I see.
All right. It seems that the original system learned the abstract notions of paddle, ball, or bricks, and it was using the patterns of pixel configuration specific to the original game to make those decisions. So it's using these heuristics to learn, to generalize. And the problem with using heuristics is it doesn't have the proper context. It doesn't have these world models. And so now we're having these debates about emergent world models. And, there's some debate as to whether models are able to learn world models on their own. So, but there's a fiery debate in the AI community on how these systems achieve their high performance. And we're talking here about modern systems, modern large language models. Have they basically memorized their training data and then retrieve it in some approximate way to solve new problems? Have they learned much more numerous and detailed, yet still brittle heuristic shortcuts? Or do they have something like a more robust world model that humans seem to use to understand and act in the world? And so Ilya Sutskever has argued that these systems have learned robust world models, but that's not a consensus view. So his case for this is that when we train a large neural network to accurately predict the next word in lots of different texts, it's learning a world model. This text is actually a projection of the world. What the neural network is learning is more and more aspects of the world, of people, of the human conditions, their hopes, dreams, and motivations. The neural network learns a compressed, abstract, usable representation of that. So this is, some people would agree with this, other people disagree, arguing that the success of large language models is more attributable to approximate retrieval from their vast memorized storage of training data. So there are some examples where we kind of are stressing the retrieval capabilities of large language models over them actually building a world model. So Jan LeCun and Jacob Browning went further, asserting that a system trained on language alone will never approximate human intelligence, even if trained from now until the heat death of the universe. Well, that's a pretty strong opinion, but you can see the point is that they're either acquiring these world models or they're not. And the world model, of course, in as much as you can define a world model, is something that, either emerges from the data or we're just simply retrieving data. And so, I guess that's an interesting question because it looks like people are split almost 50-50 on this question. And maybe we're being trolled here, but it seems like everyone, it's almost perfectly distributed between agree, weakly disagree, and disagree, with disagree having being slightly more popular than the other options. But it seems like people either are throwing darts at a dartboard or it's really contentious. So, the question is, can large language models develop emergent world models? And what is the evidence for that? So, the first step is to step back and say, what is a world model? What does it mean to have a world model? And how would it be useful to have a world model? So, a world model, obviously, if you don't give the model something like an overarching context. It has to be acquired from the data. And, maybe that's a strong sort of definition of world model in terms of, an autonomous model. If I give my model a context, if I give it some reference points in the world, is that a world model? I guess it is, but I'm giving it that information just as I'm training it on a feature space or a semantic space. So one can do a top-down sort of world model, or one can have the model acquire a world model from the data. And the question is, can the model do that through generalization, through other sorts of things, through transfer learning, etc. But we can go back to the definitions of world model, and it turns out that they're not all the same. So one definition of a world model is internal representations that simulate aspects of the external world. Another definition is representations which preserve the causal structure of the environment as far as is necessitated by the tasks an agent needs to perform. The third one is structure preserving behaviorally efficacious representation of the entities, relations, and processes in the real world. These representations capture, at an abstract level, their counterpart real-world processes, which typically involve causal relations in algorithmically efficient forms to support relevant behaviors. So this number 3 is, so these are getting longer and longer, as you can see. This number 3 is interesting because it gives some very specific predictions that the representations are, need to be there. It needs to be preserving of structure. It needs to have an effect on behavior. And it has to capture basically some counterpart real-world process. And if we go back to the idea of the Evergood regulator theorem, this is something that comes up in we have this paper on the Evergood regulator theorem or world models. Basically, in the Evergood regulator theorem, the argument is that the model has to be an isomorphic or isometric mapping to the real world. And so what does that mean? That means that the model needs to represent the real world or the world by having equivalent components. So it doesn't have to be, say, like a hyper-realistic representation where every single thing is duplicated. But it does have to preserve the structure of the real world at a level that's mostly complete. So if I, say, need to understand things in the world of Breakout, as in a video game where you have a paddle that moves left and right, you have this ball that bounces against the paddle, smashes into bricks, and then bounces back down, and you have to catch it with the paddle and bounce it back up. And the object of the game is to break through to the top of this structure. And so the idea is that the model not only needs to know how to make the next move, but it needs to know the overall goal. It needs to know what if you take one move, what the consequences, but if you take multiple moves, what the consequences for that. So you need to have all of that encoded somehow in a model. And the question is, can you learn that emergently from just kind of interactions? Or does that need to be partially hard-coded? Or, in the case of the Evergood regulator theorem, they don't really define how this model comes to be. It's often, in cybernetics, it was just often someone designing a model and implementing it in the real world. They weren't very specific on how this was done because they didn't really have any good examples. Back then, people were working on symbolic AI at best. And so you might give it of the AI a symbolic system. And, the symbolic AI systems had their own level of performance. They could do things like play chess. But of course, we moved away from those for reasons that they can't acquire data, or they can't really reason from data in the same way that our modern models can. So this is all food for thought. I'd really like to kind of think about this in terms of the ever-good regulator theorem, because I think there's a lot of instructive, something very instructive about that. So these are all definitions. These informal definitions emphasize that the world models exist in an organism's brain, or in, say, a large language model's neural network, that they capture something about the world that is causal and abstract or compressed. So it has to be causal. You have to have one thing affecting another, see the consequences of actions, know how things are related causally, and sometimes avoid spurious correlations or spurious causality. And it has to be abstract or compressed in some way that doesn't require you to reproduce every single instance in the real world, or every single component of the real world. So we don't necessarily want to have this large set of statistical associations. We want this to be compact or compressed. We want this to be algorithmically efficient. So Melanie Mitchell is the author of Artificial Intelligence, A Guide for Thinking Humans. In this book on page 236, she gives the following photo as an example of how humans model the world, including intuitive models of physics, biology, and psychology, which are these kind of models that we develop in development, or we have kind of as these sort of default models of physics and biology and psychology. Sometimes they call them folk physics or folk psychology. So it's like if you learn nothing in school about physics or psychology or biology, you tend to default to these intuitive models. And so it's just like if you observe the world, you can intuit these things. And, there might be some innate aspect to it, but it's basically very different than, kind of formally testing things through hypothesis. Just kind of making these quick judgments about the world based on intuition. So this is where, these models enable us to very quickly make sense of complex situations and understand why certain things happen, certain behaviors happen, and what causes these behaviors. So this is the picture here. This is a woman walking a dog and pushing a stroller with a child in it. And she's talking on the phone. She's doing like 3 different things at once. And, this is kind of, why is this all happening? And a model would have to take this image. Plus, there's a man walking in the other direction behind her. There's traffic. It's a city scene. Now, an algorithm would have to take this image and figure out all the components of this. What's going on, what the causality is, and what happens in the future if certain things happen. So this would be where we have to guess the relationships amongst the things in the image. We have to ask counterfactual questions, like how would the photo change if the dog belonged to the man? Or what would happen if a driver approaching a crosswalk loudly honked the horn? Or, there are a number of scenarios we can test and think about the outcomes. It's important to note that our world models don't just exist for the real world. They can also be formed and used to reason about imaginary worlds, such as those created in science fiction or fantasy literature. So this is, again, where we want to test different scenarios. We have maybe like sparse data, and we want to be able to reason about things in a way that, doesn't restrict us to those data sets. And so MIT professor Jacob Andreas wrote an insightful blog post proposing a spectrum of different types of models that might count as world models. So this is a blog post which I won't talk about, but this is just sort of a classification of different types of world models. So the first type of model that could classify as a world model, and this is the weakest type, is a static lookup table. So we all, we know that like if you're training a model, you can construct a lookup table from different entries. If you have that image that we saw, if you have different components to that image, you can take those components, look up what maybe the list of things that they possibly mean are, and then memorize, take from that lookup table possible answers, and then evaluate those answers as to their likelihood. Maybe we have more data showing the outcomes or later, outcomes in that scene. So if we have that, of course, we can, that would be maybe sufficient as a very weak form of prediction, but it wouldn't give us a lot of counterfactuals. It wouldn't be able to generalize in any way beyond the stored data. The next might be a map, such as this two-dimensional map of the solar system, where we see the planets in order, and then we see the sun, and we know that maybe that they orbit the sun. But this two-dimensional map is useful for answering queries. So if we query this model, we can get answers. We can retrieve labels. We can retrieve basic information, like which is the largest planet or which planet is closest to the sun. And this offloads a lot of the work of the world model to the user, so the user has to give really good queries in order to get a good answer. It can't, however, help answer questions like if Mercury and Earth are aligned at noon today, what will their relative positions be at noon tomorrow? To help answer questions that involve dynamics, so we have the static model, we have a lookup table, which is even weaker, and then the next step, of course, forward is this dynamics model. So this is where you have the planets around the sun, and you have like these mechanical arms. It's called an orrery. So you can actually build a model like this where you have planets out a certain distance from the sun. You represent their orbits by these rotating arms, and you can actually query the model by moving the model in different positions, moving the arms in different positions, and you can not only query things about the relationship between the sun and the planets, but then things like their relative position in their orbits. So we have a lookup table, a two-dimensional static map, and a three-dimensional dynamic map. So those are the three. And then the final model in the spectrum is the simulator. So if we have the solar system, we can have a three-dimensional model of dynamics, but that still doesn't help us with the counterfactuals. We need to kind of figure out the causal forces and which ones are truly causal and which ones are spurious. So this allows us, we know what simulators are. There are all sorts of programs that allow you to simulate the solar system and its dynamics. And so in a simulation, of course, you not only have that dynamical aspect, but you have, different alternate scenarios, different counterfactuals. What happens when? What happens if? So that's part one, and then part two is here. And so this kind of gets into some specific examples. This is evidence for world models and large language models. The case of Othello, which is a popular game. This is a simple board game. This was reported in 2022 by Kenneth Lee and others. The authors trained a relatively small transformer network to predict legal moves in the game and then analyze the internal activations in that network to see if the transformer learned a world model by virtue of its training on token sequences representing games. So basically, they trained the transformer network, which they called Othello GPT, to input sequences of legal moves and to output a next legal move in the sequence. So they trained this. They were able to generate 20 million sequences to be used as training. The input to Othello GPT is a sequence of tokens, each representing a legal move in the sequence. The correct output would be a next legal move in the sequence. This is similar to how we use large language models for language. There are certain rules to language. There are certain sequences that are more likely than others. So it's very similar. And like typical large language model training, the transformer wasn't told about anything about the meaning of the input sequence. It didn't know that it represented a game played on an 8x8 board, or that there were two players with tiles of different colors, or that players took turns, or anything else. All that mattered in the transformer's view was the pattern of input tokens. So after training on this 20 million sequence dataset, OthelloGPT was nearly perfect on predicting a token representing a legal move given a sequence of previous moves. The question was, what had the network actually learned in order to perform this task? So there was some speculation here that the transformer had developed an emergent world model, or this compressed representation of the rules of the game, and what the state of the game board would be after any sequence of input tokens. To test the speculation, the author needed a way to look under the hood of the transformer. To do this, they used a technique called probing, which can reveal whether the trained transformer's internal activations encoded the state of the game board. So this probe is a simple classifier that is trained on the transformer's internal activations to predict the state of the board at different points during a game sequence. So they created a training set for these probes. They presented many partial game sequences to OthelloGPT, and for each input sequence, they recorded the network's vector of internal activations at each of its 8 layers. If OthelloGPT had an implicit world model, these activations should somehow encode what the contents of each board square would be, given the sequence of moves represented in the input. Is illustrated below, and there's this figure here. The authors created 64 different probes. Each probe is a linear classifier. So this is where you have the true board state after different moves. You have these moves being trained to this model. You have this sequence of moves as input to the transformer. And then you have these activations from a given layer, and this is the input to each probe. So you have the A1 probe, A2 probe, C5 probe, D3 probe, H8 probe, meaning that it's basically sampling each position on the board and seeing if there's a token on that, or I guess in this case, an object in that space. So A1, for example, would be up here. That's empty. A2 is here. It's also a probe that's empty. C5 actually has a black object in it, so that's black. D3 is a white object, so that's white. And H8 is here, so that's empty. So it's basically sampling the entire board. It's coming up with an answer of what object is there, whether it's black or white, and it can do this for different after different moves, different board states, and it gets a sense of the entire space. The idea is that since linear classifiers are so simple, if they can predict the correct board state from the transformer activations, those activations must much encode that state in a very easy to decode way. They provide this representation that can easily be used to answer questions about the dynamic state of the Othello board. So remember, we don't want just a static representation, we want a dynamic representation. However, a snag arose. The linear probes trained by the authors didn't work very well in predicting the board state. This is interesting that we have these sort of static representations. We're trying to use that to derive a dynamic representation. But those linear probes didn't work in predicting the board state at any given time. So the authors tried training more powerful nonlinear probes, in particular neural networks with a hidden layer. This worked much better in predicting the board state. So activations from transformer layer 7 were given as inputs. When that happened, the trained probes were actually able to correctly predict the corresponding board state with about 98% accuracy. So this isn't really evidence for the transformer developing a world model. The problem is that the nonlinear probes are too powerful at learning patterns. And so maybe it's just the probe that's doing the predicting rather than the transformer. So, this is some evidence for emergent world models. and it's not really clear if that's good evidence or not. Some people were impressed, some people weren't impressed. I think we obviously saw that there's a split in this, and a lot of that involves sort of, you know, preferences and bias. So Chris Owa on social media said, I think the recent Othello paper was quite striking, clear evidence of a language model developing an internal world model. And Ang said, do large language models really understand the world or just give the appearance of understanding? Evidence shows large language models build models of how the world works, which makes me comfortable saying they do understand. So this is about understanding and about meta-learning, as well as about just building a world model. So this is, an ongoing debate whether or not this is an emergent world model. And, well, impressive, it's hard to say whether this is really a world model. So I don't really think that we're going to get to any consensus anytime soon on this, but it's worth thinking about world models as being an improvement on these bags of heuristics, or these heuristics, this collection of heuristics that we would typically use to make these shortcuts in learning. So we want to make these shortcuts in learning, but we don't want to do it based on simple heuristics because the error rate is too great and you come up with weird kind of associations and answers to things. We want to be able to make kind of heuristic shortcuts, but we want to do it in an informed way that understands the world and understands the consequences of actions. So this is all kind of to say that there's a lot of interesting work with respect to large language models and world models, but that I think can be generalized to other types of machine learning models as well.
I was thinking this week how important it is to step back or to visit on a daily or at least weekly level the blog. Is it like it's some play on Mystery Science Theater, but for AI?
Oh,
the who's that blog by?
Sure.
It's like Emily something.
Oh, Emily Bender?
Yes,
okay.
yes. Yeah. As well as something that who's the EFF spokesperson? He's a writer, Cory Doctorow.
Okay, yeah.
That we receive an incredible amount of marketing hype, without seeking it out, by companies who have to justify why they are still in charge.
Yeah.
by just overhype. Like a bunch of great interviews this week. So one, I thought it was interesting that the CEO of Microsoft, ostensibly to sit down and talk about how they've come out with some sort of quantum processor, which we can talk about the hype around that. But his point, and their failed rollout of Copilot.
Yeah.
His point is like, name me one thing that AI has done. Or
Yeah.
Like if this is so earth shattering, I mean it's it's funny because there's a theoretical physicist was kind of saying the same thing. I mean, she was going off on this whole like AI scientist thing.
Yeah.
Which is, if you will, an extension of that world model to, imagining the world that we can't see, right? But because we've given them enough data, that they can do these extrapolations, if you will. I think a daily dose of that is super important.
Yeah.
But the first thing that popped into my mind, which I was surprised she didn't say, was AlphaFold.
Right.
But it is really specific.
Right.
I mean, it's like you tried a key on a billion locks, and it opened one door. You don't go, this is obviously the master key, right? So it is, So I mean, this speaks to something that came from going through the references that Adam Saffron put together. Was like, hey, is this a world model, or is this, a more fuzzy concept of planning? Right. And what I love about all of this, is that I can't, it's like the last, say, 10, 12 years of AI hype has been a wonderful demonstration of everything that Douglas Adams had put into that one story about deep thought, which is, give us the answer to life, the universe, and everything, and and it comes up with an answer, and it's just like, did you actually know what your question meant? That all of this vagueness, that like every time we seem to be in a conundrum, it's really like, do we actually know what we were talking about in the first place? Yeah. And so returning to the discussion around the zero shot learning as it relates to this, right? When we're talking about cognitive development in children, we have this, like, we don't even have an internal representation. Like, we quote we come online at like 5 years old, right? Right. I mean, in terms of like what, even from our personal timeline, what are memories we can retrieve? Yeah. And that's like super vague. That's like, I lived in this city. Yeah. You can remember maybe like, I remember what my bedroom looked like. Right. And so you've got this absolute I want to use like an astronomical, like dark matter, dark energy kind of term. Like this has completely shaped your world. like you were absolutely a learning system during all of this, and a multimodal continual learning system. Right. To generate these this conceptual landscape, high dimensional conceptual landscape that you are using unbeknownst to you. Right? Like it's just the water that you're breathing in.
Yeah.
you're living in. And yeah, so I really like, I mean, Melanie Mitchell, like Emily Bender, is one of those people who just seems to come along every couple of months and be like, do any of you guys actually know what you're talking about?
Yeah.
Like what's the evidence for you saying that? I mean, other than like, a press release from a company that has absolutely everything at stake on you believing this, and I mean, again, like, it is insane to me. Um, who did a talk on this? Um, I forget if I don't know. I mean, I think the Simons Foundation and the Council on Foreign Relations both did a talk on the effect of DeepSeek on the AI landscape, or something, like, just to give you a sense of just like there was so much hype
Yeah.
going on that you get these two extremes both talking about just like, there's been a tectonic shift, right?
Yeah.
And at the same time, when you dig into the papers, this is like, this has all been just incremental developments,
Yeah.
that one particular team, for a variety of kind of like team leadership reasons, together with political sanctions, probably coalesced into this particular form, right?
Yeah.
But yeah. Anyway, so that all to say, um, well, the I certainly like, and again, this is, like, what do we get from humans behavior, but like the map is not the territory, right? So I mean, I wanted to just talk about that kind of efficiency, and as well as like some of the kind of William James um, becoming an expert on things. Like the speed at which you can answer, in a sense, out of distribution questions. Just it speaks to that kind of like, you've got this model, and again, like, I think we fall into a 3D video game kind of image in our head, but that it can actually be much more conceptual, and yeah. Anyway, it's I think, I mean, so one, I've been attending the theoretical neurobiology group meetings that Thurston runs, which are all open. You can join on Teams. The only thing is, on Mondays it overlaps with DevoWorm.
Oh yeah.
But I think he has the same structure that he used to have at the Phil. I mean, which is where he's doing it, but he's still there. But the way you do his neuroimaging meetings, where it's like, I think Mondays is kind of like an application, and Tuesdays is like theory, or is more the machinery.
Yeah.
And the Active Inference Institute started a new textbook cohort. So I attended that meeting. But I just the big difference, I think like being around Active Inference Institute, not so much, but like the machine learning street talk, Active Inference Discord, or the Discord for machine learning street talk, and then our Active Inference channel, is where you see the real disconnect between, like, here's the machinery and this is exactly what it relates to in terms of policies, in terms of math, in terms of what its extent is, and here's the vision of what people think that actually means, which is much more philosophy and what your visualizations are, as well as just bringing up how AlphaFold was considering things that were unintuitive and, in a sense, like world breaking, and again, I think that's really interesting, in that AlphaFold is one of the successes, right? Yeah, and certainly like AlphaFold's breakthrough is somewhat credited to letting go of the hand kind of handmade, human-made heuristics.
Yeah.
Which again, like, suggests that maybe our again, like, our internal world model is not actually how things work. It's
Yeah, I think that's an interesting point. And again, like in science, we have these sort of intuitive models, like intuitive physics and intuitive psychology, or folk physics, folk psychology. And oftentimes when you're teaching that, say at a university level, you're oftentimes fighting against a lot of the folk interpretations of these things. So a lot of times you'll say, this is the way something works. You'll demonstrate it through a demonstration or through an experiment. And it sometimes agrees with that and sometimes it doesn't. And so, if you're using like if you're building a world model, is the world model, I mean, I guess the question is, in the case of what we're developing as an intuitive model, is that the same as sort of a world model that's informed, or is it a world model that we acquire just to navigate the world? And so maybe the question is in biological context, you have different world models that develop from different like contexts, whether it's like someone with like a PhD level education, or someone who's trying to navigate the world, or it's some organism that's embedded in a world, in like in an aquatic environment, versus an organism that's burrowing underground, and all these things. You might have different world models, which are just ways to relate things, and that's going to have implications for how these are implemented in artificial systems. So, we talk about world models for large language models, but it totally ignores like any sort of embodiment. So it'd actually be interesting, and I haven't seen this in the embodied intelligence workshops, but someone approaching the world models question from an embodiment standpoint. That's something that might be, I think we still have time to do a submission for that. I don't know. But that's an interesting point. That maybe we have multiple world models. Maybe a world model is just a way to kind of relate to the world, and as our information changes or conceptual world changes, not just our actual world, then those world models also change. Or we have multiple world models depending on what we're doing, and there's sort of this intersection of world models, and that gives us our behavior. Again, I think that really comes down to the definition of what a world model is. So we had like 3 definitions there that Melanie gave us, and like they're all from the literature, but they're of different sizes. So like you had the 1-line definition and then the big paragraph definition, and maybe the 1-line definition is probably maybe better than the paragraph definition, but we have to define what it is. Go ahead.
Well, it's just I mean, just also thinking about that game, right?
Yeah.
Like what would a representation of the rules even look like? Or like again, and meet those criteria, like it's obviously just a toy problem.
Right.
Right, but it's also very hard for me to conceptualize what a representation of the rules would even look like, and it also just reminds me of how interesting it is when you look inside. You get some insights inside of say, a somewhat complex electrical system, and you putting a probe on some particular component, and you get very surprised by like what what range it's looking in, and what kind of like the signal looks like at that for that little component, and getting lost in all these kind of transformations and renormalizations and etc., scalings and things like that, like yeah. And I get that somewhat from some of like Distill Pub's tutorials on neural networks and things like that.
Yeah.
It's like, oh, that's what the computer's thinking about. Yeah, it's
I don't know if you've ever seen the this video. It's where Bjork, the singer, is describing what's going on inside of a television, and she's like talking about like how they're little fairies in the television that like make the image. And it's interesting because it has this relevance to a world model in that if that's your world model of a television, I mean, you could observe it, but then you could also like kind of observe the output state without knowing necessarily what's going on inside, and you have to describe it. And so, and that goes back to like when we first acquire a world model, or when we first like interact with the world, we're often kind of not observing everything, not observing the full sort of reductionist breakdown of something. So we have to kind of make explanations up. And so there's this aspect of that might be relevant to machine learning or machines or artificial models.
Well, sorry, that just also made me think about just a platonic idea of where our world models are all at best are shadows playing on a cave wall.
Right.
Right. Like we don't even have access to reality. We are yeah. This isn't in a kind of who's the guy who kind of epitomizes this UC Irvine guy, the Hoffman.
Oh, Donald Hoffman, yeah.
Yeah. That this that we're so sure is real, right?
Yeah.
Is absolutely just shadows, and
yeah.
limited spectrum, yeah. It's our own internal representation of these things.
Yeah.
Yeah. Anyway, it definitely this is all just good in terms of keep circling back to uncovering our own vagueness about these concepts, and like the engineering work is so useful at helping us be explicit, or
I also think it's kind of worth mentioning that if we do see these emergent world models and machine systems, that we should also expect to see something like a sort of a developmental phase where like they're creating these world models that are very naive, but like their attempts at synthesis. I mean, the assumption that it's going to hit upon the right world model immediately is maybe evidence that there isn't really that emergent process going on.
Well, I mean, it's again, it's also, I mean, I don't, I joke about it, but I think it's also very serious that a lot of these people have actual, not just commercial interests, but are caught up in the idea like this is the right path,
right?
And there was another machine learning street talk. Well, there was a machine learning street talk interview. I forget what his name was, but he was the original is it long short-term memory, LSTM?
Yeah, LSTM.
I always forget.
Yeah.
Who it was a very definite, why would people think that you train on all this text that you're going to get anything other than an approximate text parrot, or I mean, he was calling it just database retrieval, and there, and I'm anyway. That's why I just like I haven't checked Emily Vender's blog in a while.
Yeah.
And it's like Mystery Science AI Hype Theater or something like that. And I think Cory Doctorow maybe has to focus too much on politics these days to be shaming our AI overlords.
Yeah, and shitification and so forth.
Well, and the fact that like we're probably not going to see any anti-monopoly moves from the Justice Department this term.
Yeah.
But it is like I think you had Melanie had the Ilya quotes. I mean, he just this is someone literally raising like he's raising money,
right?
Like, of course he's saying this is the right path. Like these people are not. Yeah, it's important to remember that they're not academics, and that like there's a lot of money on the line for them. There's a big pot of gold saying this is the right way.
Yeah.
And and I think it's really, it's key to remember that, I mean, I'm not even still seeing the programming. I like that Simon Williamson, I forget his, the Django creator,
Oh,
Take your turn.
Simon Williston, maybe. Yeah.
Wilson, Wilson, yeah. But it was just like you know, yeah, where yeah, like we've got. I also like the moving goalposts on ChatGPT.
Oh
right?
yeah.
You know, so it's like when Sam Altman was forced out, was it just ChatGPT 3?
I think so. Yeah.
It was just ChatGPT 3, right? And like there was this mythical Q, or this mythical like Q star or something like that.
Oh
Like
yeah, yeah.
like you know, that they had achieved AGI. You know, there was this life form lurking in OpenAI,
Right.
and the board was scared, and you know, et cetera, et cetera. And yet, you know, we're at 4. You know, 5 is going to come along, or you know, then suddenly there's 01, 03. You know, like
Yeah.
there's all these things. You know, anyway, I am very happy to be, like trying to find this great movement from the RX, and for, you know, to have more examples in terms of you know, let's do more robot training, let's do more agent training, and by, you know, in implementations we will start to chip away at all this vagueness.
Yeah.
And you know, I don't think I don't think we're going to see anything in our lifetime.
Yeah. Well.
You know, but you know, the other meeting that I attended was the Weight Watcher AI.
Oh yeah.
You know,
Okay. Yeah.
in terms of just that's a condensed matter physicist looking at the weights without data. So it's not. I mean, it's zero shot-ish in a way.
Yeah.
Right. Well, no. I mean, it's trained, but it's it's another way of looking. It's a new way of looking at the
effects of training.
Yeah, and like the effects of training. Yes, thank you. And I'm curious, you know, and I'm really trying to get something to the point where we can see, you know, where we can have not a toy example that we can work with. I mean, he's got some MNIST kind of examples that he talks about, and he's got some vision model examples that he talks about. And but we're well, she's a researcher. Roorkee, I think, is the city in India. Yeah, IIT Roorkee, who's her PhD is focused on EEG speech decoding, right? And so Meta, you know, Meta, like again, our tech overlords are hiring up all our PhDs. So like everybody who was working on like MEG in Paris now works for Meta AI, right? And they've got a new paper on speech decoding. And but it was, it's very interesting talking with her about it, because she was, her first question was like, why did they do, they're doing speech decoding from the MEG signals, but they have the people typing. And I'm like, well, yeah, like they, like, why do you think they they had people typing?
Yeah.
And it's like, I'm like, they had people typing because they needed to know when, like that was giving them an objective. This is when I'm now thinking about this word,
Yeah.
So it's like every keystroke is giving you some insight into the timing in the neural data that you're seeing. So this is hardly silent speech,
Right.
or which again, and I was also pointing out, like let's not forget all the failed big tech projects that have tried to do silent speech.
Right.
Like there's big company here called Whisper AI that just, well, they didn't go out of business, but they've pivoted.
Oh, okay, yeah.
So and it's funny too, because they're based on this project that I still get asked about in NeuroTechX forums, Slack, or even like BCI Reddit.
Yeah.
Like, hey, I saw this MIT project where he's decoding speech by attaching electrodes to the vocal, to your neck.
Right.
I forget what that project's called, but this company is set up to do that, right? And anyway, they had something that's supposedly working. One of the reasons that they pivoted internally is that they couldn't get their own developers to use it.
Yeah.
So, and I think that also, it's another good example of, I mean, they raised a lot of money. They had a lot of, well-trained people working on this. And yeah, this was not a, practical breakthrough.
Yeah.
I mean, just another example of like, is AI changing the world?
Yeah.
It's a good practical example that we can be looking at, and we're going to do a journal club around it. We're going to build it into the software project, our MOAB software project in NeuroTechX, which is the mother of all BCI benchmarks.
Right.
So, I think it'd be cool for us to have a speech MOAB. It's like just data sets would focus on this, and it will also prevent companies. I mean, like the amount of buzz that Meta says they can decode speech,
Right.
and and people talking about, hey, did you see this breakthrough that Meta just had in terms of decoding speech? Like, they'll be able to read our thoughts very soon. And then you go and read the paper. It's just
right.
like this isn't even speech, like they're decoding,
Yeah.
And it's kind of impressive in terms of just, it's actually it's like 20 subjects, getting people to sit and type, and they needed, the other thing is, these are all trained typists, right?
Yeah.
Super trained typists, because they cover the keyboard.
Yeah. Yeah.
They don't want them looking. So these are all touch typists.
Yeah.
Anyway, it's like, not a lot of this makes it into the press release.
Oh, yeah.
That's what I'm saying.
Okay.
but yeah, I wasn't sure. You know, there's some good links in um, bioevolution, um, and Sakana has some new stuff.
Okay.
Or like Sakana's um, been releasing some things. I think they're CUDA engineer. Yeah, some stuff in dev AI, dev neuro AI. Yeah, and networks.
Okay.
Yeah.
Okay. We'll try to do that maybe next week. We'll get to that stuff.
Sure.
So this is a new paper in behavioral brain science. The nice thing about these papers is that they have an extensive discussion / critique that follows the main paper. So there's a lot of a lot of people will submit their sort of responses in the article PDF. So the main article here is going to make this sort of statement, and then people are responding to it later. We won't go through all the responses. I just wanted to go through this paper and then kind of talk about a little bit about the responses. And it's really relevant, I think, to reinforcement learning, not only simulated reinforcement learning, but this sort of behavioral aspect of motivation constructs. So this is, kind of getting into the psychology of it, but also has relevance to other things as well. So this is by Koi Murayama and Haley Jach. The title is A Critique of Motivation Constructs to Explain Higher Order Behavior. We should unpack the black box. So this is, of course, arguing that there's certain aspects of motivations and motivational psychology that are a black box, and we should understand sort of behavioral reinforcement learning in more of a cognitive way. So let's start with the abstract. So the abstract is the constructs of motivation or needs, motives, etc. to explain higher order behavior have burgeoned in psychology. In this article, we critically evaluate such high-level motivation constructs that many researchers define as causal determinants of behavior. So we usually, argue that their needs, motivations, we'll ascribe these things to higher order behaviors and ways to interpret it. But there's this sort of black box. So a lot of times when we describe motivations and other things like that or needs, we don't really have a strict cognitive mechanism to think about them. We identify a fundamental issue with the predominant view of motivation, which we call the black box problem. So black boxes are usually things that we find in science that don't have an explanation but have an output, and we try to ascribe something to that. The black box simply refers to this inability to find a mechanism, or maybe it's a some sort of stochastic process, but we don't really have a good fix on what the mechanism is. And for understanding black boxes, I refer you to the paper by Granville, the cybernetics paper, where he talks about how we can take these black boxes, break them down into their parts, thus having a clear box or a transparent box. But every time we break down a problem, we often have black boxes within that transparent box that we need to solve. So we end up either, kind of drilling down to the sort of fundamental elements of things, a very reductionist approach, or really kind of solving the black box as sort of this emergent process, which is, not always a way to sort of get a fix on what's actually going on. So but in this case, we have this black box, which is where we don't really have a good mechanism for understanding motivations. And so specifically, high-level motivation constructs have been considered as causally investigating a wide range of higher-order behavior, but this does not explain what they actually are or how behavioral tendencies are generated. So we don't know. Actually, we could break this down into sort of its cognitive psychology. We could also break this down into its neural mechanisms. So we can drill down to a number of levels here. And of course, we'll still have black boxes once we drill down, but that's sort of for another paper. The black box problem inevitably makes the construct ill-defined and jeopardizes its theoretical status. So, in theory building, we often start with a black box and we try to explain the phenomenon, and we put in these parts, and we try to take these parts and provide like a mechanism or an explanation for each part. So you often maybe will have a theory where you have these boxes that are maybe ill-defined. They have like some descriptor, and it's just merely a linguistic descriptor. We don't really know what the mechanism is, but that one thing causes another thing. So the whole point of theory building is to sort of define those things very broadly and then kind of drill down on them and find something to fit within that box. So, we usually use different mechanisms for doing that. And so that's what they're kind of arguing here. To address the problem, we discuss the importance of mental computational processes underlying motivated behavior. So they really are interested in this case in assigning some sort of computational process to these black boxes and describing maybe, like a computational model, a cognitive computational model, or a neural computational model to some of these motivated behaviors. Critically, from this perspective, motivation is not a unitary construct that causes a wide range of higher order behavior. It is an emergent property that people construe through the regularities of subjective experience and behavior. The proposed perspective opens new avenues for future theoretical development. That is, the examination of how motivated behavior is realized through mental computational processes. So that's the abstract. And so they talk about the history of this, where the constructs of motivation were mostly proposed for basic behaviors such as eating, which is like hunger drive, or mating, which is sex drive. However, later years have seen increasingly use of motivational constructs to explain higher order behavior. Nowadays, there is a plethora of high-level motivation constructs in psychology, including but not limited to the need for competence, relatedness, and autonomy, the need to belong, self-affirmation motive, desire for status, self-enhancement motive, achievement motive, and extrinsic motivation. So you see that there are all these, like, I think especially interesting is something like autonomy. We talk about that a lot in artificial intelligence. We also talk about extrinsic motivation. And that's, of course, relevant to reinforcement learning. And, these are constructs. So that means that they're not like based on a specific mechanism. They're usually collections of measures that we take when we observe, say, like a human system. So we'll build a construct out of this collection of measures. Measures actually relate to something that's like a behavioral output, or it could be a physiological measure. But then we have to understand what's generating these measures, what's generating these outputs. And that's where they're arguing for these computational models. And so drilling down on these constructs and saying this is what's causing, this is what's responsible for these constructs, instead of just thinking of these constructs as a unitary thing that we can't really explain at the level of prediction or control. well, I guess we can explain it in terms of prediction, not necessarily control. So this is what we want to get to. So they talk in this opinion article, we provide a critical analysis of these motivation constructs to explain higher order human behavior. Specifically, we cast doubt on the theoretical status of high-level motivation in the sense of a construct that directly influences complex behavior. Rather, we contend that such high-level motivation is a subjective construal or emergent property of underlying mental computational processes which determine behavior. From this psychological construction perspective, we clarify both strengths and weaknesses of high-level motivational constructs and offer a new avenue for research that has attracted almost no attention in the past, and that is theoretical analysis of how motivation is realized through mental computational processes, not just measured as an output of behaviors, but or a collection of measures, but as this sort of mental computational process, which is active, and being able to explain that process. So I want to go down to the open peer commentary because, there's some interesting things here. So, oftentimes these commentaries can add a lot to the original article. This one is called Endogenous Rewards, a Bridge Between Social, Cognitive, and Behavioral Models of Choice, which is where they talk about intrinsic reward at will, or endogenous reward is a fiat currency that is occasioned by steps towards any goals that are challenging and are common enough to prevent its debasement by inflation. A theory of mental computational processes should propose what properties like goals grow from appetites for endogenous rewards, which may be the universal selective factor in all modifiable mental processes. So this is one. Another one is this resurrecting the black box conundrum. The abstract here is in this article, Murayama and Jach contribute that contend that a mental computational model demonstrates that high-level motivations are emergent properties from underlying cognitive processes rather than instigators of behaviors. Despite points of agreement with the author's critiques of the motivation literature, I argue that their claim of dismantling the black box of the human mind has been constructed on shaky grounds or shaking grounds. Basically, that this is not the correct way to view this. And so, how do we dismantle this black box? This is a classic discussion in psychology in particularly with respect to how accessible is what's inside the black box. So can we access the black box? And, using a set of computational processes may or may not get us there. This one here is exploring novelty to unpack the black box of motivation. And the abstract here is Murayama and Jach point out that we do not sufficiently understand the constructs and mental computations underlying higher order motivational behaviors or motivated behaviors. Although this may be generally true, we would like to add and contribute to the discussion by outlining how interdisciplinary research on novelty-evoked exploration has advanced the study of learning and curiosity. This one is motivation needs cognition, but is not just about cognition. The abstract here, Murayama and Jach offer valuable suggestions for how to integrate computational processes into motivation theory, but these processes cannot do away with motivation altogether. Rewards are only rewarding because people want and like them. That is because of motivation. For example, sexual desire is not primarily a quest for rewarding information. Elucidating the interface between motivation and cognition seems a promising way forward. So then this one, the unboxing has already begun. One motivation construct at a time. The abstract here reads, Murayama and Jach argue that it is not clearly specified how motivation constructs produce behavior, and that this black box should be unpacked. We argue that the authors overlook important classic theory and highlight recent research programs that have already started unboxing. We feel that without relying on the mechanisms that such programs uncover, the proposed computational approach will be fruitless. This one is, it's bigger on the inside, mapping the black box of motivation. And this is many motivational constructs are opaque black boxes and should be replaced by an explicit account of the underlying psychological mechanisms. The theory of motivational systems has begun to provide such an account. I recently contributed to this tradition with a general architecture of motivation, which connects energization and direction with the goal-setting activity of emotions and serves as an evolutionary grounded map of motivational processes. So this is, they insert their sort of theory in here, where you have these different cognitive, perceptual, and attentional processes, and these aspects of goals and mood and motivational systems here, emotional mechanisms, action selection, and so forth. This one is expectancy value theories contribution unpacking the black box of motivation. The abstract reads, although in basic agreement with Murayama and Jach's call for greater attention to the black boxes underlying motivated behavior, we provide examples of our published suggestions regarding how subjective task value and ability self-concepts get into people's knowledge structures. We suggest additional mental computational processes to investigate and call for a developmental and situated individual differences approach to this work. And then the last one I'll do is needed clear definition and hierarchical integration of motivation constructs. And the abstract here reads, Murayama and Jach offer a thoughtful and timely critique of motivation constructs. We largely concur with their basic premise, but offer additional input and clarification regarding the importance of carefully considering the energization and direction components of motivation and fully attending to the hierarchical aspect of motivation rather than prioritizing particular levels of analysis. So that's a nice overview of that, and I didn't get into a lot of the jargon, but there are a couple points here. One is, I covered some select responses, and I think they cover a lot of territory with respect to, kind of there are disagreements, there are agreements, there are suggestions from the literature, how to extend this, and so forth. The second is, you can see how these kind of debates work, going back and forth, how, you're introducing new concepts and kind of figuring out the right level of, adjustment to existing theories. And then three, this notion that we have these constructs for something like motivation and how we can augment them with computational models, with other types of description, and then conceptual advances that make that better. And then how that can maybe relate to artificial systems where we're building models of motivation, say like in an artificial system, in a reinforcement learning system, and how those models can be improved by what's going on in psychology and in sort of the psychological science, and then bringing that over into artificial systems.
Well, yeah, I certainly wanted to bring up, because it seemed like there was, quite rightfully some supporting references from child development.
Okay.
But how neurodegeneration is actually an interesting field as well in kind of elucidating the mechanisms of motivation when they fail, or when they are themselves degraded, and yeah. So I saw some references to motivation versus cognition, or the like interplay of motivation and cognition in child development, as certainly trying to unpack the relationship and kind of the complexities. But yeah, there's just interesting work in terms of, again, what what I'm calling computational psychiatry. But what I just mean by that is, these trying to model these behavior changes that happen, whether it's a disease process, whether it's age, healthy aging, or whether it's neurodegeneration. What you see in, like exploitation versus exploration, for instance, right? So older adults, as you might imagine, stop exploring.
Yeah.
And it's not necessarily that they know what to. It's a really interesting topic, and obviously, something I've been trying to say, like, these artificial systems lack, right?
Yeah.
And again, just, I mean, it doesn't even, it almost doesn't bear repeating, but just the these artificial systems are so far from being alive.
Right. Yeah.
Like the thing I've got no more time for is is a large language model conscious?
Oh yeah.
Yeah. But what it certainly lacks. Again, there's there's people talking about large language models cheating.
Oh right.
Right, and it's just like, they're not cheating. like again, like that word, that word doesn't make any sense.
It doesn't make, in the context, right?
Anyway, but so it's a wonderful topic, and I saw that there was a reference in the original article to Yalniv. So I want to check that. She's got some 2006 trends in cognitive sciences that I'm sure would be an interesting read on motivation.
Yeah, I'm not familiar with motivation as a whole, so I'm not really, I don't know the literature that well, and I didn't know some of the terms necessarily. But I'm really, what interested me about this paper was kind of like how we have these different constructs to explain behaviors. And, they're not like in cognition, we usually do we have like memory, we have things laid out in kind of a conceptual model or a theoretical model. And then in attention, we have the same thing. And then we try to attach measures to it. And we try to do, neuroimaging. And like with motivations, it's kind of like this is something that's motivating people. And there's a kind of a theory behind it, but it's kind of very broad in terms of, it's kind of cast as an overarching explanation for, and I know people have like different computational models, like based on dopamine and things like that. But it's a little bit different than what they're talking about here. Yeah.
Yeah. I mean, so one, that's the big criticism of cognitive science, right? Is what they actually mean is adult cognitive science.
Right. Yeah.
Right. Like adult abstract cognitive, like abstract thinking cognitive science.
Right.
And the developmental psychologists are like absolutely super familiar with motivation.
Yeah.
So, they're coming at it from there's this wellspring of activity. What's driving it? And we so it's again, I think there's no surprise. I mean, I just kind of saw some references, but like there's a lot of cognitive development references I think, in this because of that, and that they're going to talk about a split as in kind of older children, where cognition and motivation actually become more separated. And like the cognitive scientists aren't incorrect to have not thought as much about these motivations, because there's actually this split,
Right.
And then there's all these important, in the kind of Karmeloff-Smith post Piagetian understandings of, like, we really do have these critical periods of cognitive development, or we have these periods of cognitive development where there's like massive reorganization of the underlying systems, or and that like, unless you are studying kids, I mean, her big point was like, looking at kids pre kind of 7,
right?
Which is also interesting, because of course this is what we know from neuropsych, where it's just like, if you have massive cortical damage before 7, then your brain can shift. You've got massive hemispheric damage, that your language function can return, for instance, but it's like after 7 that won't happen,
right?
Or like again, to link it back to the kind of neural underpinnings, like you said, with dopamine and things like that, like we know from damage that there's obviously something going on too, right? Anyway, it's interesting. I got the PDF, and I'm gonna check that out. Yeah, for sure.
All right, that sounds great. Okay, well, thanks for attending this week, and hopefully we continue on with the Slack. We'll try to review the Slack next week. So,
sounds good.
All right, see you. Thank you.